Our first keynote lecture will be provided by David Long. David Long lives in Blacksburg, Virginia. He is the founder and the president of Vitech. In 2014 and 2015, he was the overall president of Incosi. And today, he will talk about the role of systems engineering now and in the future. David, great that you're here. The stage is yours.
Thank you, David. I truly appreciate the warm welcome. I've followed SwissED a bit from afar for the past 5 years, and it's a pleasure to actually have the opportunity to participate in this wonderful national event. So 2 things about my background before I get started, because they're often misunderstood. As David said, I was the 2014-15 president of Incosi. What that truly means is I simply do not know how to duck. I missed the opportunity when it came through. All joking aside, it was a wonderful period of time, but what it provided me, what I reflect upon greatly, is not only the opportunity to connect with colleagues around the world, but the opportunity to talk with organizations about their needs, their challenges, their approaches. Second aspect is I am an ESEP. I was very pleased to see the systems engineering certification advertised out front. That simply means that I've been doing this for a long time. Again, I think certification is very, very important, and it reflects where we go as a practice and a discipline. What I want to talk about today is part of that journey, a part of the journey that we honestly are obsessed about in systems engineering, model-based. Before I get too far into it, I need to understand you a little bit better. How many would classify themselves as experts in model-based systems engineering? And there are a couple in the room, okay? See, I've got to be careful now because these people will call me out if I make a mistake. How many consider themselves practitioners? They're active practitioners of MBSE. More hands? MBSE aware? Can spell MBSE on a good day. Okay. One way or another, don't worry, this presentation is for you. So as I noted, as a profession, we are somewhat obsessed with model-based and now digital. In 2016, at the International Symposium in Scotland, I counted up the papers, and a full 25% of the papers had MBSE as a key part of their title or their abstract. When you consider a field as vast as systems engineering, that's a tremendous percentage. The second number these days is system of systems, which is down in the 10 to 12%. So before I get into where we're going, we need to talk about where we are. And we need to talk about why we're here. But as good systems engineers, there's something even more important that we should begin with, and that's context. Because with the wrong context, you can come up with the right solution to the wrong problem. All good systems engineering is fit for purpose. So if I were to ask you in a word or two, what is the unique characterization of problems that systems engineers get involved with? How would you characterize what is special about our problem set? Anybody? Complexity. Very, very good answer. The number one answer on the board. Necessary, not sufficient. There are many people who deal with complex problems. Chemists, physicists, etc. It's an aspect, but it's not the defining aspect. Anybody else? Bridging disciplines. Exactly right. David touched on it when he said connecting people. Systems engineering at its heart is transdisciplinary. We used to say multidisciplinary. In the most recent Incosi definition, they've adopted the term transdisciplinary, which I truly appreciate because multidisciplinary can be in their own silos, live apart. As was said, it's about bridging. We are the technical connective tissue that brings together teams that solve problems that cannot be solved by one discipline alone. So if it's complex but lives purely in the chemical domain, we don't bring value, we do not get involved. We help study the problems from multiple perspectives, link the team members, share the insights, come to common understanding of problem and solution, hopefully minimizing unintended consequences, maximizing emergence through the whole life cycle. That's our critical context. We have to remember that. So within that context, if we look back through the history of systems engineering, for a long time, we were solving what at the time we thought were complex problems. Today, what we would characterize as complicated problems. So this is the era of Apollo. This is the era of the 60s, 70s, into the 1980s. If you're to take a product lifecycle management view of the world, systems engineering is there on the fuzzy front end. We help properly characterize the problem. We understand the requirements, the architecture, both the functional and the physical, and then we bridge in to the solution. In doing so, we are able to partition the architecture along rather clean lines. And I'm not an expert in complexity, but the simple way I will define complexity versus complicated for this audience is, in complicated, you may have many piece parts to your system, but there is very low coupling, very few interconnects between those pieces. So if you build those pieces properly and bring them together, you have reason to believe that the system will work. And that served us very, very well for a long period of time. Put spacecraft in orbit, did many, many other things. But when I was INCOSE president in 2014 and 2015, a wonderful document was published by INCOSE. I take no ownership of it, but I truly value it. And it is the Systems Engineering Vision 2025. If you have not read it, it is still worth a read. It is still completely relevant 5 years since. And it says this. There was a classic chart that noted 6 primary challenges. I've listed 4 here. First is complexity continues to grow. Mission complexity specifically, but more than that, also technical complexity. The complexity of the technologies that we're using is completely different than what we did in the 50s, 60s, and 70s. So in many ways, the systems engineer and the systems engineering team are caught between 2 forms of complexity. Second, as much as we wish it to be otherwise, most architectures are accidental. They are assembled rather than designed and engineered. And so what's the result? We have systems that are very difficult to operate, very expensive, very brittle. Who would like to go to their customer and say, do I have a deal for you? I'm going to build something that's hard to use, it breaks often, and it's way over budget. Commission me to do your work. It's the antithesis of what we want. The third is we know we lose a great deal of information throughout the life cycle of a project. If you think of ISO 15288, from conceptual design to detail, from detail to production, from production to operation, maintenance, and ultimately retirement. Doesn't sound like a very good way to run a project. And fourth, we fail to learn. We fail to learn across projects. And during my INCOSE presidency, wherever I went in the world, when I talked to organizations involved in systems engineering or wanting to get involved in systems engineering, sadly, they resonated with each one of these points. Why? It's because we have started to exceed the bounds due to complexity. It's the system scale, it's the system scope, it's the technologies in play, and I'll come back to that. It's the team structures. No longer are we dealing with one organization that is building these systems. We're dealing with large organizations, multiple organizations, and oftentimes across multinational boundaries. And there's even dynamic complexity. The problems are changing as we try to solve them. By the way, it's worse than just complexity. Not only are the problems getting harder, we're being asked to do more in less time. What we used to have years or months to do, we're now asked to do in weeks or days. Lots of pressure, and we're exceeding the bounds of what served us so long. So this is what drove our profession to model-based systems engineering in the early 2000s. Now, there's a challenge. There's a problem. There's been great progress, but, well, it was well-intentioned, but flawed. Where we stand today, we took a well-intentioned approach to the problem of complexity, to solving those 4 challenges I noted, but we've put ourselves on an island. How? Why? If you think back to the 1990s, What characterized the era of systems in the 1990s? Anybody? I'm sorry? Data. Essentially right. We changed the technology, the fundamental implementation technology in the 90s moved from electromechanical to software centric, software intensive. Why does that matter? Because in the age of electromechanical systems, we had very low coupling between the pieces of the solution, the pieces of the architecture. In today's modern systems, we have electronics that snake throughout, and even worse is the software that runs on it. So we now have highly interconnected, highly interdependent architectures. Okay. In that era, we noted that there was a problem in our understanding and our communication across the implementation cycle. If they are going to software intensive systems, we must improve our ability to communicate with the software engineer. And so in the first era of what we now call model-based systems engineering, or in the first official era of what we now call model-based systems engineering, we decided to better handle complexity, we need to adopt new techniques, and we need to adopt techniques that close the gap with software engineers. Well-intentioned, but what's our fundamental context? Our job is to be the technical connective tissue, not with software, but with all. David noted it earlier. We reach from the owner to the user, to the manager, to the subject matter expert, to the manufacturer, to the through life logistics. We have to serve all of those people. And unfortunately, we put ourselves on an island. That's okay. We can leverage the insights and the tremendous advances over the last 15 years, but we have to recognize it's time to get off the island. Now, John Holt, for the closing plenary, has a wonderful title, MBSE in one chart, because MBSE, in my opinion, is so misunderstood, so muddy. I always have MBSE in one chart. John, you can grade me later on how well I do. I'm sure you will. So here's MBSE in one chart for me. What this change is all about, if we really reflect on the challenge and we really reflect on the context, is not about a particular technique. It's not about a particular notation. It's not about a single stakeholder. It's about changing the way we fundamentally represent knowledge. Because in the days of complicated and rather static systems engineering, perhaps a specification, a document was good enough. It's not good enough now. We can do better. So how can we better represent knowledge in a more consistent, coherent, connected manner that serves the entire stakeholder community as we are this technical connective tissue? In doing so, we can take advantage of modern computing techniques and computing powers. That's it. That's all. It's about how can we better represent knowledge in a more actionable way. Now, actionable has two dimensions. As systems engineers, it's important to serve both the communication aspect and the analytical aspect. As an engineer, I want to put the analysis first. As a systems engineer, I must put communication first. If I fail to help the team achieve shared understanding of problem and solution, nothing else I do matters. We are about connecting people. So I must first achieve shared understanding, communication through actionable knowledge, and in the process, I must handle the additional aspect of analysis. If we do it right, we can achieve the so-called authoritative source of truth. We used to say single source of truth. We now say authoritative because we recognize it may be distributed. In doing so, I can use modern computer-based techniques to ensure consistency. Inconsistency is deadly. Consistency is what we're after. And I can connect the greater environment. Now, in doing this, I also change the way we frame this. Why? I intentionally try to simplify it. There is a lot of fear, confusion, and doubt. Fear, uncertainty, and doubt about MBSE. It certainly seems mystical. It certainly seems hard. Well, in some ways, it's common sense. In many ways, it's an evolutionary journey. If I can lower the barrier of entry, then I can bring more on that journey. So MBSE is just about changing the way we represent knowledge to a more coherent, more consistent, more actionable manner. How can we do that now? How can we build upon the progress of the last 15 years, yet return to our real context and solve these complicated problems? There are many things if we look to the greater context. We now hear terms digital thread, digital twin, digital engineering, MBE, SysML v2, etc. Well, the interesting thing is, if you peel back the covers and look beneath, many of these groups are going to the same fundamental idea, and they've arrived at it largely independently. That's good. That means that truth likely lies along that vector. So what are these approaches? Well, at the US Department of Defense in 2018, they kicked off a digital engineering strategy. Okay, that's simply one group, one country, one industry. But that digital engineering strategy is being reflected and leveraged by organizations across domains, automotive, energy, medical, and it's being used around the world. In old terms, we would have actually called this model-based engineering. It's not model-based systems engineering. That's just a piece. That's in fact the upfront conceptual design and the technical connective tissue at the technical layer, at the digital layer. But this is through life engineering. How can we change our engineering approaches to be digital from cradle to grave? It's important to note here that models are just a part of this. Infrastructure, culture, and most importantly, workforce. It's about the people. If it's about knowledge representation, that's a fundamentally human problem. So it's not just a technical issue. Now, I need to stop here to take a little bit of a muddy sidebar, because we often get ourselves in trouble. Even though systems engineering is about clarifying communication and reducing risk, we haven't done a very good job of it ourselves. And so if I were to ask you, what is the definition of model? Just the loose definition of model, what would you say? Anybody? A representation of something real. Colin, you're my straight man here. You're perfect. Thank you. So if that's true, and that is the perfect statement, anything short of the real entity itself that generates some communication or analytical value is therefore a model. Okay. So is a computational fluid dynamics representation a model? Absolutely. Is an electrical circuit a model? Yes. Is an activity diagram a model? By this definition, yes. Is a document, is a specification a model? Yes. So if everything is a model, then what's model-based systems engineering? We chose our terms badly. It happens. Now, I don't say this to create a religious war, nor to create a quest for the next great term. That's a complete waste of time. I say this simply to indicate, if you're talking to somebody about what MBSE is, you need to understand their terminology, don't debate it, but understand what they mean, because I've watched us talk right past one another, because everything is a model. And so what's model-based systems engineering? It's the formalized application of models. Okay, that's good. That's okay, good news. Digital engineering is to the rescue. So what's digital? Is a Word document digital? Is a PDF document digital? The answer is yes. But again, they're not actionable. So terminology will get us in trouble. Don't go on a quest to solve the problem, work around the problem. Not all MBSE is created equal, because people simply use the terms to mean different things. And by the way, as long as it's fit for purpose, I'm okay with it. We have to solve problems in a fit for purpose way. So be careful of the terminology. All right, let's move on. So we've got multiple groups who independently are shifting our context in a good way. If you look at SysML, so SysML is kind of the default language, the default notation, I would say, for model-based systems engineering. And so the team is currently working on V2. And this is a true version 2 level effort. It's not a simple update to earlier versions. It's not version 1.5, 1.6, 1.7. It's a fundamental change of scope to say we live in this greater ecosystem. How do we connect the engineering of systems? How do we take the great progress that we've made with V1, all of its variants, and build upon it and in fact change it where necessary so that we lower the barrier of entry and we bring more value. We enhance the communication value. We enhance the analytical value. We expand to handle verification. We do all these things. So if you look at where V1 is headed, it talks about these concepts: a new meta model, robust visualizations that engage more stakeholders, standardized API so that we can serve as a connective backbone. Same concepts that were in the Department of Defense Digital Engineering Strategy. Current timeline, initial submission, June of next year, finalized version, June of 2021. This is a vast undertaking, a grand scope. There's one more. So digital engineering is now what we used to call model-based engineering. SysML is going to V2. There was something written in 2018 called a model-based engineering manifesto. Note, it's not an MBSE manifesto, it's an MBE manifesto. And they followed the precepts of the Agile manifesto. By the way, for those who fall into the trap, the manifestos do not say A instead of B, they say A over B. We will value information over the artifacts, specific artifacts that represent that information. It is far more about integration, our ability to bridge, than it is about independence. It is far more about expressiveness with rigor. We have to communicate clearly in semantically meaningful ways over flexibility. And if you simply finish your creation of model on the last day of your project, you've derived very, very little value. It's about the usage, the exploitation over model creation. And it is in the context of engineering from first concept through retirement. Multiple groups have looked at it and said, to solve today's problems, we have to change the scope. We have to better engage. We have to better connect people. And systems engineering is a part of that. Therefore, as we go to MBSE 2.0, we must live within that context. So how do we transform the engineering enterprise? How do we really make this possible? How do we move from our techniques that were built for complicated world and live within this complex world? Well, the first thing that we have to recognize is we have to change our perception of the engineering lifecycle. If it is about connecting people, if it is about the fact that our systems, because of the technologies that we choose to use, because of the technologies which bring great power, but also complexity because of the coupling, we can either fight against it and act as if it does not exist, or we can embrace it. To run this mental model is the ostrich with its head in the sand, acting as if coupling does not exist. No longer can we act as the all-knowing upfront systems engineer or systems engineering team, issue independent specifications, be them in document or model form, to teams and think that we're going to get good outcomes. Because the reality is there's high coupling, there's high interaction between these teams as we move forward. Attempting to do it this way is very slow, very risky, very costly. So what's the alternative? The alternative is shifting to a mindset that respects the interconnection. What was digital engineering, the digital engineering strategy after? What is SysML v2 after? What is the MBE manifesto after? It's recognizing that the design space, the architecture space, is truly highly coupled. If the systems that we build are highly coupled, then the system that builds it must be highly coupled, and the system's process must be highly coupled. We can reject that at our own risk, at our own folly, or we can embrace it. Again, it is a human problem. It is a workforce challenge. It is a knowledge representation challenge. But right at the heart of this is the systems engineer. Because who is the technical connective tissue? We're not the most important, but we are that technical connective tissue that binds these teams together so that we can come up with shared understanding of problem and solution. We can understand the thermal impacts of that change. We can understand the electromagnetic interference impacts of that change. We can understand the impact of a little change over here, okay, in the Boeing 737 MAX that has a ripple effect that we could not see before. And in doing so, if we bind these teams together in a higher fidelity way, we can oscillate, iterate across these interfaces very, very rapidly. So together we come up with the main architecture. That architecture is then the connective tool, the digital connective tool that binds the subsystem teams together. They can engineer their piece in context. They can understand the first, second, third, 23rd order effect of their solution. What does that mean? It means it changes the equation. Regardless of the term that you choose to use, I like to go all the way back to fundamentally, it's about engineering of systems. If you like digital thread, digital twin, digital engineering, MBE, that's fine. It's about the engineering of the system. To do that requires concurrency. We cannot separate because of the coupling. Concurrency requires a concurrent variant of MBSE, what I will call MBSE 2.0, this next step. And it has to be in the context of digital engineering MBE. It's maximized by, surprise, surprise, re-engineering the engineering enterprise. We cannot take the current sequential life cycle and run it as is. Will not work. By the way, that's built upon a holistic systems perspective. We have to take the perspective that we use for the solutions that we develop and apply it to the environment, the organization, the enterprise that is engineering that system. Let's break down MBSE 2.0, concurrent MBSE, just a little bit more. We have to be concurrent in 3 dimensions. We have to be concurrent in what I would call the model-based dimension. Let's simply say this is the ability for systems engineers to work concurrently together. Okay, we're solving that to some terms better, to some terms worse, but we're fundamentally solving that in today's modern environments. Any team of a like discipline learns how to work together. The next challenge is the S. Can we effectively engage all members and stakeholders? This is where we have to get off the island that we accidentally created in 2003 when we focused only on the one implementation technology. Does not mean that we have to reject, we can build upon, but we have to get off that island because the perspective of all user, operator, customer, subject matter expert is essential. And the last D is pretty important because it is engineering. So can we effectively engage detailed design within the engineering of systems? If these systems, if the subsystems, if the architectures are highly coupled, is a small change over here truly a small change in systems performance, Or does a small change over here fall prey to the butterfly effect and have a tremendous unanticipated impact on system performance? Because of the interconnects, it's too hard to tell without going concurrent. Okay. The fundamental behind all of this, the keystone, is not the knowledge representation. It's not the artifact. It's the information model itself. Now, if you wish to call this an information model, okay. If you wish to call this a meta model, that is my chosen term, but I would amplify it that it needs to be a semantically precise, meaningful systems meta model. If you choose to use the dreaded O word, ontology, that's fine too, because technically this would be an ontology. Just do not fall prey to large academic ontologies. This is an engineering problem. We cannot handle a scale of 100,000 terms. That's too big for us. We need a much smaller set. But there's a fundamental information set necessary to successfully engineer a system through life. One of the problems with systems engineering is we have yet to define it. Pick up the MBSE handbook. It's there throughout, but it's never actually defined. What the MBSE handbook is, which is very valuable, is a series of processes, methods, and tools to elicit and manage and analyze the information necessary to engineer a system. But nowhere have we defined the information necessary to manage the system. We use many of these terms. They're not new to us. We know what requirements are. We know what functions are. Okay. If you're bored one day at work, gather a systems engineer, a software engineer, and an electrical engineer in the room, and have them define the term function. What you will find is a term that is somewhere between 95 and 98% common. That 2 to 5% variant is very dangerous. So we need to define these terms, but more than that, it can't just be a taxonomy of terms. We are about systems engineering. Systems engineering is about interrelationships and interactions. That's where the emergent value of systems comes from. That's where the negative unintended consequences come from. The same thing is true in systems engineering. So it's not enough to define requirement and function. We have to define what we mean by the valid relationships. In doing so, we've got far more than diagrams. Diagrams may be ways to represent a subset of this for a particular communication purpose, but a diagram is semantically ambiguous. I don't care how precise you make the notation. It cannot be rich enough. It's not about a data dictionary. Everybody's got a data dictionary. That's just the individual data objects. We're systems engineering. It's about the interactions. It's actually more than capture. If you have this, it serves as a map, and it allows you to move from what you know to what you don't. And it's more than specification. The interesting thing is, even in today's model-based world, we obsess about the specification that we hand off downstream. That is only a part of the value. The design journey of how you got there is essential to downstream decisions, and it's even more critical to change. If a requirement changes, if a new capability is desired, your specification is perhaps only a quarter of as valuable as the analysis that led to that specification. So we need to capture the design journey in this process. If we do this, we do not need to discard MBSE 1.0. MBSE 1.0 largely feeds this information model, this meta model. It can represent the meta model, but the shift is moving very explicitly from a focus on artifact to a focus on actionable information. Because the actionable information can be represented in fit-for-purpose ways for that greater context within the digital engineering environment. If you wish to satisfy SysML v2, if you wish to satisfy the MBSE manifesto, if you wish to satisfy digital engineering, you cannot do it without a semantically meaningful systems meta model. And I'm going to go one step further. There's a trend out there now called define and use. People recognize the importance of a meta model. So they, on their project, will define and use a meta model. Oh, that's fine for your project, but not for the discipline, not for learning across projects, not for us as a practitioner base, not even for your enterprise. Because if everybody chooses to speak their own dialect, then are we truly communicating? So it's not about the artifacts, it's about the information, the engineering necessary to engineer systems. If we do it properly, we can represent in any fit for purpose way. But where does this take us? Well, it takes us in a need for a convergence. There are multiple paths here. Vitech is on one. We trace our history back to work that was done by a group called TRW, now part of Northrop Grumman. Ballistic missile defense dates back 50 years of practical application. There are a number of industry effects. So if you're a member of INCOSE, the S-STAR meta model, the patterns-based systems engineering working group, effectively has a meta model. DODAF, Department of Defense Architecture Framework, UAF, SysML, these all have meta models. The key is we need to converge upon an essential core. Yes, you're still going to need to change it because the exact semantics necessary to engineer an insulin pump are different than the semantics necessary to engineer a fighter plane. But the concept of requirement, function, interconnect, those are the same regardless of what you're talking about. What does this do for us if we achieve this? Well, first off, we can recognize change happens. Change is currently disruptive. If, however, we have the information across design coupled, we can assess the impact of change. There are many techniques that attempt to package it, and those are good, but we have to recognize if a new requirement comes in. If my competitor has just deployed a new battery that changes the range of the automobile from 300 kilometers to 350 kilometers, and I now, for marketing reasons, need to go 400, how do we do that? Today, it's actually very, very difficult. Highly coupled, if we match the coupling of the engineering enterprise semantically with the engineering of the system, we're okay. We recognize one of the challenges in SysML v1 is actually the connection between behavior and physical architecture. A system it has a manifestation even if only in software, and a system does, it performs a function. Well, if those two are interconnected, should not their knowledge representation, should not the architectural engineering be interconnected? What does my component talk to? What are the interconnects with the other subsystems? What does my component do? How can I capture that? It's actually quite basic, but we have to get back to choosing to define a meaningful systems meta model. If this serves your purpose, great. If not, if you wish to use the pattern-based working group work, great, but don't move forward without one. Perhaps my favorite example is this. If we look at how we traditionally specify capabilities, let's say I'm building a UAV, an unmanned autonomous vehicle, and I wish to have a specific range. I wish to have a specific loiter time. And so in my all-knowing system design, which is probably attempting to solve an over-constrained problem, but in my all-knowing system design, I tell the battery subsystem team, you have a mass budget of 10 kilograms. That's the best I can do based on what I know. And in that becomes part of the technical data package, along with their requirements, their interfaces, the constraints, in this case, mass, etc. In a classic 1.0 world, in a classic document-based world, what happens if the best that that engineering team can do is 11 kilograms? They're non-compliant. they've got two choices. One is to come back and ask for relief. Two is to explore new technologies, different technologies, perhaps ones that are not at the appropriate technology risk level, technology readiness level, perhaps ones that are more expensive and will break the cost curve of the system. But in a classic linear flow, there's not a whole lot of flexibility when the subsystem cannot live within the constraints, the requirements delivered. What happens in a concurrent world? Well, if we go a step further and we provide the physical and the behavioral context, if we tell them, how did we arrive at that 10 kilogram value? Why is that so important? The analytical dependencies. What if we give them the literal equations that allow them to test system performance at a technical level? What's 11 kilograms do? It may devastate the range, or it may have little impact. But also, not only the system performance from a technical level, but what about the system value function? How does that interact with the cost value? If my choice is I can do 10 kilogram for a high cost or 11 kilogram for a low cost, boy, now I've got a lot of insight that I can bring my perspective and help us deploy the best possible system. The issue is that subsystem team still does not have flexibility. They do not have the right to violate the design envelope that they were given, but they can do analysis to understand what the impact of their design choices are, what the impact of the art of the possible is, and they can have a more informed conversation at the higher level. We can't have those conversations today. And if we stay on an island, we never will. We've got to get off the island. We have to recognize our role in this connected engineering environment. The last thing I noted was that systems engineering has to be both for communication and for analysis. Oftentimes, you can split the models into the descriptive architectural and the detailed analytic. The descriptive architectural are the ones that allow you to characterize the system from need through architecture through test. The analytical are the ones that allow you to bring the rigor of engineering. We can't separate those. That is a false division. So what if they can truly be bound together? And this is one example. There are many, but if you take a technology like Phoenix Model Center, you can interconnect those. You can use the system level model, if it has good semantics, as the technical connective tissue through parametrics that bind together all the engineering analysis models that let us know what's possible. So it's not new technology, it exists today. Fundamentally, if we do this right, we can connect all the way from our systems back upstream to the operational analysis. What need are we truly trying to solve in the marketplace, whether it's defense or commercial, all the way back up to strategy. These same concepts repeat in either a recursive or a fractal pattern, depending on how you prefer, because in each level, we're talking about the move from statement of need to approach to implementation. And then at the strategy level, implementation becomes the statement of need at the operational level, and on and on. And we can understand if we changed our strategy, how would that force us to change our systems? Our enterprises are as interconnected as our systems. It's time for us to recognize that. It's time for us to recognize that if we want to engineer modern systems, we must re-engineer the modern enterprise. So what do we get? We get the fundamental authoritative source of truth. We have the connection of architecture and analysis. We have health, resilience, and safety, system-level concepts through pattern and architecture. We have the chance at composability. Let's come back to the challenges. So we've got 4 primary challenges. We've got complexity, lack of architecture, loss of knowledge, and lack of learning. If we apply this mindset, if we properly execute SysML v2, the MBE manifesto, digital engineering, and we recognize that MBSE with a proper semantic foundation should serve to bind all of those together to successfully engineer a system, what happens to our challenges? Well, in place of the challenge of complexity, we now have a semantically meaningful representation of knowledge, which we then couple with fit-for-purpose representations. Why? Because we have to achieve shared understanding of problem and solution. If I do not know my place in the systems team, I do not understand the impact of my change. And sadly, if you want to look at many system failures, it traces to that. So if we better represent our knowledge and take advantage of computing techniques simply at a descriptive level, we can better address the coupling and complexity of our systems. But we can do better than that. Now that shared understanding gives us a chance to have resilient and elegant architectures. Because if I unlock the understanding of every member of that team, systems engineering is transdisciplinary. It's the perspective that I overlook that will get me in trouble. If I can unlock those insights early, boy, what an opportunity. A great systems engineer in isolation is worthless. A great systems engineer as the interconnect of a good engineering team is priceless. What about knowledge? Well, that's where the authoritative source of truth comes in, but we have to have both design and rationale. It's not enough to understand the endpoint because change will happen. If we truly have that authoritative source of truth, you know where to go to, you know what truth is. We still actually don't know that today. And then between projects, well, now we've got knowledge retention and organizational learning, because as you complete a program, you can play it back and you can say, what learnings do we feed into our engineering approach, to our technical approach? How do we create block 2, V2, the next upgrade? Because the best starting point is the existing systems model. But it's only useful if you've got a shared semantic model. How do you take this back? How do you do something today in your organization? 4 steps. First, actually, I'm going to put a step 0 on this chart. Fit for purpose. Your engineering has to be fit for your system in your business context. What I use for a man-rated space system and what I use for a telecommunication device that's allowed to drop offline for a second, those are actually 2 different approaches. So first, understand your purpose and your business context. Then look across the silos. If this is about bridging, if this is about connecting people, if this is about living within the system's context, we have to understand who we're supposed to connect. Understand where you are in the journey. You do not have the opportunity to build your organization from scratch. You have to do a transformation, and that's much harder. So what is the as is? And what is the aspirational to be? And you can't take the entire journey in one step. So what's the next small step that you can take? Implement a semantically rich systems meta model. Please do not go invent your own. The last thing that we need is the 101st, 102nd, or 103rd meta model. What we need to do is start a convergence. If Vitech works for you, take it and tailor it. It's open domain. If the pattern-based working group works, start with that. But please start from something and tailor. And last, start today. You can sit, you can wait, you can watch, but complexity is not slowing down, change is not slowing down. And I can tell you what, our competitors and our user demands are pushing us up. So begin today on this V2, on this MBE, on this digital engineering environment, on that journey, and recognize the role that MBSE 2.0 must play. Thank you.
David, thank you very much for this. Sorry. Thank you very much for this very interesting session. Now we open up to the audience. We have still a few minutes left. Are there questions?
The back here, in the middle.
Yes. You described a little bit about how the earlier modeling languages led to some difficulties because we put ourselves on an island,
Yes.
and how we've improved that by better interconnecting across the teams. Can you describe in a little more detail how some of the modeling languages have already done that?
So the answer is the modeling notations today have not largely done that, okay? Because the modeling notation that we chose, if you make the false equivalence of MBSE equals SysML, then you have picked a notation that is easily embraced by the software community and by systems engineers who are trained in it, but nowhere else. So what we have done today, certain organizations and certain environments are attempting to put a semantic backbone behind that with different levels of success. And with that semantic backbone behind it, then they're using other visualization packages, et cetera. So at the language level, we're not there yet. People are doing workarounds. Others have a semantic backbone. The question is whether or not V2, et cetera, moving forward will.
Can I ask a follow-up then?
Please.
Given your experience in the industry, what would you suggest in moving forward with, for say, for example, a medical device company? Just as an example. Would you go with the semantic backbone you described, or is it more just
Yes,
workarounds?
I would, regardless of what your application domain is or what your system's maturity is in your organization, I would always recommend that you begin with a semantically meaningful meta model. Now, I would be careful how I frame that, because even those terms are going to cause most people's eyes to glass over. So all we're after is saying, all right, guys, what's the fundamental information that we need to elicit, manage, and analyze to deliver? Put it in terms that people can understand. But the reason that I always start there is if you reduce systems engineering to recognize that you're after that information set, that, regardless of how you implement it, gives you the skeleton upon which to hang the right processes, methods, and tools. If you don't do that, then you're at the will of either the senior systems engineer, who may or may not be right, or you're just picking from a toolbox and you may or may not be right. It turns out, if you don't overcomplicate it, if you start with that information model, you make systems engineering a whole lot more understandable.
Thank you.
Yep. Front. There we go.
Thank you. You were talking about concurrency in the engineering.
Yes.
Still, I believe some sequencing is important. You cannot let start everyone as he wants. These couples to the other aspect you said, architectures are very often rather driven by components, reuse or whatever, than
Yes.
a top-down thinking through. Still, I mean, both ways, the concurrency as well as the components-driven architecture, create a lot of problems, which we tried with a V model or otherwise to
Yes.
overcome. So I think concurrency, yes, but still we have to do something to keep the focus and reduce entropy in the thinking.
No, you're exactly right. And any statement about process, concurrency, or linear is a simplification. The answer is reality is both. The point I'll make here is actually, let's go back to the V model. The V model is perhaps one of the most misunderstood models of systems engineering that exists. And many people, in talking about model-based systems engineering, say, this is important. We can't afford to run the linear journey through the V any longer. It takes too long. We must blow a wormhole through the middle of the V. People who speak that way don't actually understand the V. If you go back and you speak to Moos and Forsberg, the creators of that, again, it's a simplification. But if you look closely at the V, you'll recognize it's not a linear journey across that V. There are bands on the V. And what Moos and Forsberg were trying to communicate with the bands is do it in levels of abstraction. There is both concurrency at a level of abstraction, but then you must be able to somewhat lock that down before you move to the next level of abstraction, the next level of detail, et cetera, recognizing that there's iteration that's occurring between them. If you do model-based systems engineering or digital engineering correctly, what you're doing is you're trying to take a V that currently is flat like this, because you can't ascend the right side of the V until you've got first article for test. What they're trying to do is tighten the V up to this, because through digital techniques, you can try to digitally verify early and often. But your point is spot on. Even my comments are an oversimplification. It must be concurrent and sequential, just wisely.
Because time is a bit low. But be assured, David will remain here the entire day.
I'm around.
Industries now invest money in product lifecycle management system. How would you implement SysML2 semantics well in such a system on a building block or a function on so basis?
With great difficulty. And I don't say that to bypass the question. It's a function of the specific product lifecycle management system, but it's a function of more than that. So first off, many PLM systems are actually more geared towards artifact management than information and interconnect management. And so as we try to take the semantically rich information that we're after and connect it properly, which we must do, we have a disconnect. What does that mean? It means that we've got to re-engineer the PLM capability as well, not discard it, but we have to have more capability. The other aspect is there's a difference between PLM and engineering. PLM is often implemented to capture the outcome of engineering, and the engineering enterprise itself is a highly collaborative. So what we have to do is layer DE, digital engineering, on top of a PLM backbone, because PLM serves a very critical role, but PLM must evolve from where it is today to a more information semantically rich, granular structure for us to do this. It's a journey on our end, on the systems end, and it's a journey on the PLM end. The good news is both bodies recognize the journey. The question is, do we come together to ensure the interface works? Thank you.
Good. Now we split up into 3 streams.